Welcome to Probability and Statistics. In this lecture video, we're going to talk about Chapter 3.3, the measure of relative position. The first objective I want to go over is the percentiles. In a couple lecture videos ago, we talked about something called the median, what lies in the middle. So if the number median is what lies in the middle, that means that numerical value is actually used to divide the data into two 50 percentiles, okay? Because this number is what lies in the middle. So it divides your data up. So what we can do is use percentile. The idea of a percentile is to describe where the data actually located. Okay, one individual data, where does it locate in your whole entire data? So the formula from the textbook here describing how do I find the location of a data value. Okay, so the L, the lowercase L here is the location. So all we do is take the number of sample times the percentile, okay, the percentile divided by 100. So when we're using this formula to find the location, okay, you must make sure to follow these two rules. If the formula results in a decimal value for the L, okay, the location is the next larger whole number. If the formula results in a whole number, the percentile value is the arithmetic mean of the data value in that location and the data value in the next larger location. So let me show you what this is trying to say. Okay, this is kind of very strange. Follow these two rules. So if I just look at the formula to find the location of percentile. Okay, so here's my data. Given the following data, find the diameter that represent the 53rd percentile. So I'm looking for what number here is actually what lies at the 53rd percentile. So what I can do, okay, what I'm going to do right now is list these from small to the largest, okay, real quick. 1.3 is the smallest one. I'm going to try to list from small to large real quick. So if you can just bear with me a minute. 1.32 is the next one. 1.41 is the next one. 1.41 again is the next one. 1.47, 1.49, 1.51, 1.56, 1.59, 1.59, 1.61, 1.64 occurred three times, excuse me. Maybe I'll go back a little bit. I'm trying to fit all this into one screen if I can. 1.64 occurred three times, and the last one 1.68. Okay, all right. So 1, 2, 3, 15 number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so I got 15 numbers listed here. 53rd percentile. So who is the 53rd percentile? So we take the number of sample size 15 times 53rd percentile. 53rd percentile is 0.53. So if I multiply here, 15 times 0.53 is 7.95. 7.95. 7.95 is a decimal. Okay, so what this referring to is the 7.95 place. Okay, or 7.95 number. So the rule says round to nearest whole number. So I'm going to say eighth number. What is my eighth number that I listed? 1, 2, 3, 4, 5, 6, 7, 8. So 1.56 will be the number that lies in the 53rd percentile. Okay, so that's my answer, 1.56. Okay, that's what this problem is trying to say. Which data value lies in the 53rd percentile? Okay, it's the 8th number, which is 1.56. All right, vice versa. Percentile of a data value. Okay, so this time we're gonna have a data value. Okay, see what the location is. So L really represents the location of your data, divided by sample size times 100. So we're gonna do this backwards a little bit. All right, so let me go back to the previous example. If I want to find, for example, I'm just making this up. All right, what is, all right, the 10th number? You know what? Let's go a little further out. The 12th number. The 12th value. Okay. What percentile would that lie in? So this is 8, 9, 10, 11, 12. The 12th value is this 1.64. That 1.64 lies where? So to find the percentile, all I'm going to do is take my number, my 12th number, divided by, all right, how many data I have, which is 15 data. That's what the formula says, L over N. Then I'm going to say times 100 to convert into percent. So this 12th number, which is 1.64, so 12 divided by 15 times 100, that will tell me this number 1.64, this very first 1.64 lies in the 80 percentile. Okay, so that's what the percentile means. Give you find the location of your data. So like I said, median is a numerical value, okay, that lies in the middle of your data set. So that number will divide your data into two 50 percentile. Okay, so if I go higher than the 50 percentile, all right, if I go higher than the 50 percentile, so that means that numerical value will be, that data value will be a little bit after that. So 53rd percentile, if you're actually trying to find the median for this example, take the ends off to find the median. Work my way inward. The 1.56 will actually be the median. Okay, so the 53rd percentile is right after the median. All right, so this numerical value actually lies, you know, about 53rd percentile, the 8th number here. Alrighty. Now let's try this example. Okay, this example has a lot of parts to it on the homework, so I kind of divide this thing up a little bit. We will do one more of these toward the end. Alright, so the problem gives you all this information. The mean salary, we gotta make sure we see all this wording. The mean salary at a local industrial plant is this much. The standard deviation, okay, plus or minus $4,400. Okay, so that means on average everybody make about $27,000, give or take, plus or minus $4,400. The median salary is that, and the 61st percentile numerical value is 29,300. All right, so with all these information given, approximately 61% of the salaries are less than or equal to 29,300. True or false? Yeah. So in other words, what does the 61 percentile mean? The 61 percentile of the data, okay, if we list from small to large, 61st percentile is $29,000. So that means everybody before the 61 percentile, or everybody before this 29,000, is actually less than or equal to. So that is true. Just like how I listed. Okay, everybody before the 53rd percentile is actually less than or equal to. Okay, because we're listing this from small to large. All right, so that's true. All right, same information. Let's figure out what this means. Joe's salary, okay, is $35,000, and Joe's salary is 1.9 standard deviation above the mean. What does that represent? Okay, we will come back to this problem. Okay, we will come back to this problem. I'm going to show you something toward the end of the video to answer this question. All right, let's go on to the next one. Same information. Okay, based on the given information, the percentile rank of 26,400. Okay, what does 26,400 mean? That's the median salary. So the percentile for the median is 50%. That is true. That's what median is. Median is right there at exactly halfway point, 50 percentile. So that's true. All right, interesting question here. Same information, but approximately 11% of the salaries are between these two numbers. Okay, so the 26,000 is the median. The median is always going to be at the 50 percentile. The 29,300 is at the 61 percentile. Shouldn't say 50%, 50th percentile. So approximately 11% of the salaries are between these two numbers. So that gotta be true, because you go from 26,000 to 29,000. That means you're going from 50 percentile to 61st percentile. So the difference gotta be 11%. So that means there are 11% of the data lies between these two salaries. So that would be true. If you just subtract them, it will be 11%. Alright, so that's what percentile represent. It's just a different way to look at your data. Very important concept. Okay, and a lot of this stuff we are talking about right now also reflect back to the empirical rule. Okay, the empirical rule that we talked about in the last lecture video. Okay, the mean is right there in the middle. The mean is separate your bell curve shape into two 50 percentile. Okay, one standard deviation away above or below the mean covers 68% of your data. Okay, go from one standard deviation to the next standard deviation. Okay, in one little area that will cover so many percent of your data. All right, and we will talk more about that as we go along, about that empirical rule. Objective number 2 here, we're going to divide our data, break out even more, something called quartiles. Quartile is referring to dividing your data into 4 equal parts. So each quartile contains 25% of your data. And what is so-called the 5-number summary is referring to the minimum value of your data, the smallest data value you got. Quartile 1, median, quartile 3, and the largest data value you have. So you got 5 numbers here, which will actually be, and what's in between them is your quartiles. First quartile, second, third, and the fourth quartile will actually be in those space right there. Okay, so these number, so the Q1 is the number divided up, okay, between the quartile. So is median, so is Q3. Alright, so if you read this thing, this is how to find quartiles. Okay, by hand. So basically, if I go back to that very first problem we did, all right, we found earlier the median is 1.56. Okay, so before the median, this is your first 50%. To find Q1 by hand, all you gotta do is find the median. Okay, find the median of your first 50%, which is 1.41. So that number is Q1. This is your minimum. The very last number got to be your maximum. 1.56 was your actual median. Okay. So you see you got numbers in between Q1 to Q3. 1, 2, 3, 4, 5, 6, 7. Yep. Behind the median. Okay. Behind the median. Find another median. So that will be 1.64. Q3. There you go. 1.64 is Q3. So this is your 5-number summary. Okay. Divide your data up into quartiles. Okay. Alright, so show you how to do this in the calculator. We don't do this stuff by hand much. We put it in the calculator. We're gonna go back to stat, edit, and typing all our raw data under L1. You cannot find a median. Cannot find median with a grouped data. If you group them into class, you actually do not know exactly what each data value is. You only have some approximation using midpoints. So you really cannot find a median of a grouped data. Okay. So just keep that in mind. Keep that in mind. Alright, so for example, calculate a 5-number summary. So I'm going to put this in the calculator. I'm going to go back to stat, edit, typing these numbers. Alright, got 10 numbers here. Once I key it in, I press stat, go back to the word calc. Okay, 1 variable statistics. I'm gonna do L1 only. I only got number under L1. So if your calculator look different than mine right here, if you have an X list, put L1. If you have a frequency, just don't put anything. Okay, highlight the word calculate and press enter. So just like how we find standard deviation, variance, simple mean. Okay, it's the same process. So here my mean is 79.3. Now I need the 5-number summary, so I will go down. See right here, go down. Minimum X is 61, Q1 is 72, median 79, Q3 88, maximum is 95. So this is your 5-number summary. That's how you find it. Alright, your minimum. Is 61. Q1. The median. Q3. There's no Q2. Q2 is your median, basically. And your maximum X value. I'm gonna write it down. The maximum was 95. 72, median 79. And Q3 was 88. Alright. Alright, your 5-number summary. Alright, let's go down a little bit. Alright, an outlier. Okay, this word coming very popular in statistics. An outlier is a data value that is either extremely large or extremely small compared to everybody else. So outlier can occur due to human errors, because maybe we wrote down the data value wrong, something like that. Okay, so we normally do not include an outlier. Okay, to check for outlier, okay, by using quartiles, we got to first understand this word called the interquartile range. Interquartile range is referring to range of the middle 50% of your data. So what you do is take your quartile 3 number minus the quartile 1 number. So back to this example. Alright, if I have an interquartile range, IQR is referring to my Q3 88 minus my Q1. And 88 minus 72 here tell me my interquartile range is 16. Okay. Alright, so for me to check for an outlier, okay, we use something called the lower fence and upper fence. So you take the Q1 minus 1.5. 1.5 means 150% outside of your interquartile range. That would be the lower fence. Q3 is, upper fence is Q3 plus 150% times your interquartile range. Okay, so for example, is more than 100% on the test an outlier? So here I got 110. So we're trying to see whether this 110 grade is an outlier or not. So if this number falls outside my lower or upper fence, it will become an outlier. So I'm gonna go back to the calculator. I think I got all the number here. 88, 95, 61, 72, 69, 80, 91, 82, 77. And I want to add 110 to it. Okay. So once I add 110 to it, my minimum, maximum, all those 5 number summary will change. Okay. So let's redo this. Alright, the mean is 82.1 now. So I'm going to go back here and copy down what I type here. Alright. So let's see what changed. Minimum 61, Q1 is 72. Median now is 80. My Q3 is 91. And the maximum is 110. So before I do my fences, I'm going to find the interquartile range, which is take my Q3 minus my Q1, 72. My interquartile range is 21 points. Alright. So for the lower fence, that would be Q1 72 minus 1.5 times the interquartile range 21. Alright, your upper fence. Take Q3 plus 1.5 times your interquartile range. So basically what we are doing mathematically is expand 150%, give an extra 50%, okay, from the lowest and from the highest value. 72 minus 1.5 times 21. Lower fence is 40.5. anything lower than 40.5 would be considered as an outlier. What about the upper? I'm gonna just go back and change this number. Just take 91 plus 122.5. Alright, so that would be my upper fence. So my highest number, my 110, is actually inside the upper fence. So if it's inside, okay, then it's not an outlier. So can more than 100 to be an outlier? Yes, it can, as long as what? If it's an outlier, it means outside of the upper and the lower fence. If it's within it, you allow it. Okay. If it's within the fence, it's not an outlier. If it's outside, okay, it will become an outlier. So that all depends on your data itself. Okay. All right. So exactly what we do with this 5-number summary, okay, another use for the 5-number summary is constructing what we so-called a box plot. Box plot is just another graph, okay, that we use to describe the distribution. Okay. It's another way to describe the distribution. We're seeing something called skew right, skew left, uniform, and the bell curve shape. Box plot is just another display. Alright, so what we're going to end up doing is, once we draw this box plot, we can use the median and the interquartile range to describe the central tendency. Okay, that's the reason why the IQR was very important, because the interquartile range is 21. This is from Q1 to Q3. So we want to see, basically, okay, this is the center of your entire data. Okay, so that's why box plots you use to describe the central tendency. All right. So once we drew this on the number line in the calculator, you can begin to see it, the way how things are being skewed. Alright, so with the number I have in my calculator right now, okay, I'm going to show you how to do this box plot. Alright, I'm going to start over again, okay. I already got the number in here. I'm going to do calc, one variable statistics. Alright, I got to make sure I got these numbers displayed before I do the next step. Alright, press second stack plot. Second stack plot. Choose number 1. Okay, my start plot 1 is turned on, so press enter. Come down here, choose your box plot. Okay, there are 2 of them. This one or this one. Okay. The first one will display your outlier if you have one. Okay. The next one does not. So I'm going to choose this one. All my data was under L1. There was nothing under L2. So my frequency now is 1 at a time. Oops, sorry. Press alpha and number 1. Okay. It's the same thing as when we did the histogram, kind of like. Except right now I don't have anything under frequency L2, so I'm gonna put a number 1 here. Alright, before I graph, press zoom, choose zoom stat. I'm gonna go up. It's number 9, zoom stat. Here we go. That's my box plot. Alright, so if you look at this number line, you know what? Let me do it this way. Nah. Let me put a number on here. Alright. So this is my box plot on the number line. So the very first number is the minimum, which we say was 61. Alright. The Q1 is the beginning of your box. And Q1 was 72. Q3, I think, was 91. This is the end of boxes. Is your the end of your box is Q3, your maximum 110. and the median is right here in this line. Median was 88, I believe. 80, excuse me. Okay. So we draw a box plot so we can see the distribution, the central tendency. All right. So this thing on this line here is a little bit longer than that. So it's almost, this box is almost located at the center of this x-axis. You know, a little bit skewed to the right, but not much. Okay, not much. Skewed to the left would be like way over here. Okay, or the tail is very, very long on the right. Okay, this one is not that bad. Now, what box plot really tells us, okay, is the mean. Your mean is an approximation of your mean. The mean was 82.09, and this 82.09, this mean will always be inside the box plot. Will be somewhere in this box, okay, which the actual mean is slightly right behind the median. Okay, just another way to describing your data. Some textbook call this the box whisker plot. You know, the whisker on the cat. These two lines look like a whisker. Okay, it's called a box whisker plot. All right, let's try some example here. Let's just look at it. By looking at this box plot, is the data skewed to the left? That means the tails. Remember, this is about the tails. Does that have more tail on the left, more tail on the right, or is pretty symmetric? All right. To me, it looked very symmetric right here in the center of this number line. All right, this one. This is a good example. A high school has 32 players on the football team. The summary of the players' weight is given in the box plot. Approximately, what is the percentage of player weight less than or equal to 234? 234 is right here, and that number is your Q3. So how many players weight less than or equal to 234? So that's referring to everybody before the third quartile. Before the third quartile, the percentage got to be 75%. The third quartile is where the division of the 35%. So everybody before here is 75% of the data. Okay. I'm gonna wrap it up this section with this very, very important topic. It's called the standard score, or called the z-score. Okay, so this is a transition from basically from descriptive statistic to inferential statistic. Okay, using the concept of a z-score, because we're going to begin to analyzing our graphs and expand it from the sample to the population mean. So this is the beginning of it. So what's going on is this. I'm gonna bring back somebody from last lecture video. In 3.2, I believe, we talk a little bit about this empirical rule. Was it here? Yep. Where let's go to another page here. All right. If you look at this empirical rule, all right, the mean is always right here in the center, and I ask you to memorize the 68, 95, and 99.7%. All right. One standard deviation to the right, to the left of the mean is 68%. Two standard deviation is 95. 3 is 99.7. Now, this thing is standardized. Basically, this thing can be is already standardized because the 68, 95, 99.7 is already set. The only thing changes is every different problem you will have a different mean and a different standard deviation. But as long as your bell curve shape, it will always fall back into the empirical rule. So standard score, or called the z-score, means we have another axis where we say the mean is 0. And this 0 means how many places away from the mean. Just like the problem that I showed you before. Where is it? Okay. This example from 3.2, the mean of the test score was 84. Now, when we subtract the mean, when we take the individual data, subtract the mean, we get this distance from the mean. If one of the distance is number 0 here, that means that data value is the same as the mean. So that's why the distance will be 0. So here right now, okay, how many standard deviation away is from a mean to its mean? 0 place. So to the right one will be 1 standard deviation above the mean, 2 standard deviation above the mean, or 3 standard deviation above the mean. If you go to the left, first one will be 1 standard deviation below the mean, 2 standard deviation below, or you can have 3 standard deviation below. Okay, so these are called the z-scores. We standardize every single problem we have, okay, into what we so-called the z-score. Okay, that's what we're trying to do. So the z-score is referring to the distance that the data is from the mean in terms of how many standard deviation away, not how many places away, how many standard deviation away. Okay, positive z-score means data is larger than the mean, negative means it's below the mean. And your formula, the z-score is always your x value minus the mu divided by the standard deviation, sigma. Or for the sample, that would be x minus x bar, the sample mean divided by the sample standard deviation. So the formula is the same, it's a different notation. One is describing for population, one is for sample. Alright, so for example, if I have a set of data where the sample mean is 37.2, so that means my x bar is 37.2. Now we are beginning to write down all these numbers and see what they stand for. Sample standard deviation, S, is 6.5. Alright, calculate the z-score given that this data value x is 29. Alright, so my z-score is equal to if you look at the formula, x minus x bar, so that will be my 29 minus my x bar 37.2 divided by how many standard deviation, which is 6.5. So we will subtract first, which is negative, no surprise, because 29 is below the mean, divided by 6.5. Round to 2 decimal places for z-score, negative 1.26. So negative 1.26 is referring to 1.26 standard deviation below the mean. So negative 1.26, if you go back to this picture, negative 1.26 will be slightly right below what? 1 standard deviation. It will be about right here in that spot. From that spot to the mean, 1.26 standard deviation away. Okay, to standardize all problem into the z-score, it makes the computation a lot easier. Alright, So I got this problem here, and I also had another one. I skipped it earlier. Let's go back and visit that old one right here. So this example is saying Joe's salary, $35,000, is 1.9 standard deviation above the mean. Is that true or false? Well, the mean is $27,000. This is Joe's salary, so Joe's salary got to be X. The sample mean is the X bar. The sample standard deviation is the S. So is Joe's salary become 1.9 standard deviation above the mean? So that just means we gotta find the z-score. That's what that problem is saying. So for your z-score, we take Joe's data value minus the mean and divided by the standard deviation. And let's see what that is. Subtract first, divided by 4400. Voila, 1.9. So yes, Joe's salary is 1.9 standard deviation above the mean. So this answer, true. Okay, that's what's going on. So every different problem that we face can be all convert. You can convert your X value. What we're doing here is convert the X value, okay, into a standard score or z-score. So we standardize this entire x-axis. So the percentage doesn't change, okay? The percentage never change. So is this z-score spot never change. What change is the sample mean, which is always at the center. But different problem have different mean. But as long as you're a bell curve shape, you can always fall back into this picture, the empirical rule. That's why we can standardize it. Okay. Even with different numerical value from different problem, as long as we are bell curve shape, we can standardize every problem back into something like this. All right. So this last one, same information. Okay. If Tom's salary has a z-score of 0.8, how much does he really earn in terms of dollars? So this is a little bit backwards, because earlier we convert Joe's salary into a z-score. Now we need to do it in reverse. So I'm giving you a z-score, which is already 0.8. All right, if you think about this formula, you got 4 things here. To find one of them, you need the other 3. So right now I need to find the Tom's salary, which is X. So I need my mean and my sample standard deviation. So my X bar will equal to my X bar is equal to my mean 27,200. My sample standard deviation S is 4,400. So if we just plug into the formula, this is going to be 0.8 equals my X, I don't know. Tom's salary, I don't know. Minus the mean, 27200. And divided by my standard deviation. Okay, so let's do a little bit of math over here for a minute. Okay, cross product. Do a little bit of cross product. The point A here can be viewed as 0.8 over 1. Okay, 1 times x minus 27,200 is still going to be the same thing. Set equal to, multiply diagonally, 0.8 times 4,400 which is 3520. Alright, to get x by itself, we will move the negative 27,200 to the other side, or you can say plus 27,200 on both sides. Okay, either way, my answer plus 27,200 times salary, 30,720. Okay, that's how you do this problem. Alright, and we will talk a lot more about this, okay, after chapter 4. We do a lot of z-scores. Alright, that will conclude this video presentation. Thank you for watching.